let's quickly go through some applications of these induced currents. And these are all really important applications that would require a lot of time and some more complicated math to get into in great detail. So they're kind of being introduced here, and you might see one problem on each of them, but we can't really go into detail at this level of physics. So the first one is the idea of a basic generator. And I mentioned when we covered motional EMF that the idea of a generator is that you're taking motion and turning it into electricity. So now this should look to you just like the basic motor, where you have these external magnets that is creating your magnetic field. And notice that we're assuming that these are creating kind of a uniform magnetic field, just for simplicity. But now, instead of pushing a current through the wire, which makes it turn, we have to do something else to make it turn. So you imagine some sort of force pushing it, or some sort of torque is a better way to think about it. And what could cause this? Well, you could have a wind, right? This could be attached to a big turbine. This could be water also going through a wheel. This could be just a fan over some coal you're burning. But one way or another, you're making this turn, usually by putting some big fan blades, kind of on this side of it. So that makes it turn. What happens then is over here, we are inducing a current as it turns because you're changing the angle that it makes with the magnetic field. And then as you're inducing that current then flows through this circuit. And so you're getting a potential difference, or an EMF. Now notice that it's sinusoidal. Why is it sinusoidal? Because what you're actually changing here is the angle. So this is basically sine of omega t, because that corresponds to d dt of cosine of theta, if theta is changing in time. Now, one thing to notice is that this doesn't give you the same sort of voltage that you get from a battery. This gives you something sinusoidal. We call this alternating current, AC. That's actually what comes out of your wall. We're not going to study this in this class. It mathematically becomes very complicated very quickly, but we have to talk about it a little bit right now with some of our applications. But again, recognize that the current that comes out of the wall is AC. So when we say that a generator creates AC, that's actually really useful because that's what we need. DC is what batteries create, and it's not necessarily what we get out of the wall. So this is the idea of a basic generator. In this case, we're going and taking motion and creating current with it. And again, it really does look like a backwards motor. That's absolutely true. So then we have a transformer. The idea of a transformer goes back to that very first Faraday experiment that we talked about, where you have an iron core, also called an iron yoke, that is connecting two coils together, not electrically. It's just allowing the magnetic field to kind of stay trapped. It keeps the magnetic field between these two coils rather than letting it spread out. And in this case, you have, again, AC. This does not work with DC. But you have one voltage going up and down in a sinusoidal way, and that creates a different voltage going up and down in a sinusoidal way. And the amplitude of this depends on the number of turns. So now this is one way of writing the equation. You could also imagine writing it this way, which I think is how the book did it. You can rearrange this however you want, but this is a way of actually changing the voltage. So why is this useful? So for instance, the high voltage lines running around our country can have thousands or hundreds of thousands of volts on them. That's not what comes out of our wall. So those like power plant stations, you'll see them on campus, you'll see transformers on power poles. The idea is we send around the country high voltage, but then you step it down using a transformer and make it lower voltage to come into your house. So again, this is working to change voltage. That's how we would think about it in this class. Something that the book doesn't mention that I'll mention is that the power is actually maintained if you do this right. So we can't create or destroy energy. So power is actually always the same. So if voltage is changing, current also changes. So if you increase your voltage, that actually means that you decrease the amount of current. But to think about that in detail, again, we need much more advanced circuitry and math than we're doing in this class. So the takeaway here is this pretty simple equation, which you can play with a little bit, but this is a really important application. Again, you'll see transformers around your house, around your neighborhood, around campus, and this is a really basic model for what they do. Okay, the last application actually uses eddy currents. So when we talked about eddy currents, we talked about how they can be used for braking, like a train. Another application is actually metal detectors. Now remember that eddy currents will occur in any sort of conductor. It doesn't have to be magnetic. So this is how metal detectors can detect copper or aluminum, not just iron. The idea is that you have something that is creating your field, and then if you put metal between it, you get those induced currents, which kind of blocks part of the magnetic field, right? The induced current itself. And so the receiver then would have an induced current, but the amount of induced current depends on the eddy currents. So this is kind of a neat thing, right? So you're creating this changing magnetic field. That's what the transmitter's doing. You're then inducing eddy currents, and then those eddy currents create their own magnetic field, which is inducing in the receiver. So when there's significant metal in between, you get an induced current in your receiver, and you know that there's metal there. Now, I'm not going to claim that this is actually how the metal detectors work at the airport. This is a pretty simple model, but hopefully this can make sense to you and you can see why this is a neat application. So there are some other applications, but again, most of them get very complicated. So expect that whenever we do calculations with this material, that the calculations are going to be very simplified. It's really hard to calculate the real world scenarios that correspond to these ideas.